This video is produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. In this video we will be looking at series. A series is a sum of terms from a sequence. So for example, if we take the geometric sequence from the last example in the last video, which was t sub n is equal to 3 times 5 to the power of n, the terms were given by 3, 15, 75, 375, and so on. Geometric series that corresponds to this sequence is denoted by S sub n, and it is equal to t1 plus t2 plus t3 plus t4 plus so on, all the way up to tn. So S1, which is equal to t sub 1, we don't add anything on, is equal to 3. S2 is t1 plus t2, which is 3 plus 15, which is 18. And S3 the same, we add the first three terms, which gives us 93. So we want to be able to work out S sub n for any arithmetic or any geometric sequence. So can we find a general formula for Sn for the underlying sequence when it's arithmetic? So if we try just off the bat, and we'll write down S sub n is equal to a, which is the first term, t1, plus a plus d, so a plus d is the second term, which is t2, plus a plus 2d, which is the third term, t3, so on, and so on and so on. When we get to the very end, where we get a plus n minus 2 times d plus a plus n minus 1 times d. So we've captured all of the t values here, but just written them in terms of a and d. What we'll do is we'll write this series again, but in reverse. So we're going to flip the series around, and the first term will now be the last term, and the last term will now be the first term. And we're going to add it to the original series, the original Sn that we had. So we'll look at that in the table below. So the first row, Sn is equal to a plus d plus and so on. And we see that this is the original S sub n written just as it is above. Then down below on the next line, Sn is equal to, we can see that instead of a we have a plus n minus 1 times d, which is the last term. And the second term now is the second last term, and so on. And the last term is now the first term from the line above. So all we've done is swapped the series around. The first term is now the last term, the second term is the second last term, and so on. What we're going to do is add these together. What we end up with when we add Sn plus Sn on the left hand side, well, that's just 2 times Sn. And we notice that every time we add these together, so we're going to add the first term with the last term, that gives us 2a plus n minus 1 times d. We'll add the second term with the second last term, gives us 2a plus n minus 1 times d, and so on and so forth. And we end up with every single one of these additions being the same thing. And we also notice that there are n columns here, so we end up with n of them. So what that tells us is 2 times Sn is equal to the addition of all of these numbers together. But as they're all the same, and there are n of them, we can rewrite that as n times that number, 2a plus n minus 1 times d. This implies that Sn is equal to n over 2 times 2a plus n minus 1 times d. And this is the general formula for the arithmetic series, which can be found in the tables book. So what about if the underlying sequence is geometric? What can we do? Again, we'll start with the same, that Sn is equal to a plus ar squared plus and so on. So these are our t1s and t2s and such, just like with the arithmetic, but instead we have our a, our first term, and r being our common ratio this time. So we're going to multiply the sum by r, term by term, and compare it with the original. So we see this is our Sn written out as normal. And now we have r times Sn. So what we do is we multiply by r and we shift all of these just one step to the right and add them in this fashion. So what we've done is we've subtracted the second row from the first. So this takes advantage that most of these terms are the same. So we can subtract the second from the first and see that most of these terms actually end up cancelling out. The only things we actually are left with is the a from the first position and the ar to the power of n from the last position. So when we subtract the second row from the first, you can see on the left hand side we are left with Sn times 1 minus r, so we factored out the Sn. And on the right hand side we have just an a minus a times r to the power of n. So what we do is we let these equal, we factor out the a on the right hand side, and we end up with S sub n is equal to 1 minus r. Sorry, S sub n times 1 minus r is equal to a times 1 minus r to the power of n. And what this implies is by dividing both sides by 1 minus r, provided r isn't 1, is that Sn is equal to a times 1 minus r to the power of n all over 1 minus r. And again, this is the geometric series that you'll find in the tables book. So let's look again at the geometric series formula. S sub n is equal to a times 1 minus r to the power of n, all of that over 1 minus r. But what if the series is infinite? Because what if we had an infinite sequence and we want to add infinitely many terms together? So this is equivalent to n approaching infinity, i.e. the number of terms are getting closer to infinity. Now if r is a fraction between 0 and 1, then r to the power of n will also be a fraction between 0 and 1. And furthermore, r to the power of infinity approaches 0 as n approaches 0. So what we can say then, as n approaches infinity, s sub infinity is equal to a all over 1 minus r. The reason being that as n approaches infinity, the top line will just become a.